All right, so we'll kind of start off, kind of remind us where we left off, and then we'll transition into not looking at the difference in sample means, but looking at the difference in sample proportions. So we'll kind of focus on that today, work through a few examples. We'll probably start on the Excel. We'll see kind of time-wise how far we get into it. But before we get going, so last class, we started doing confidence intervals for the difference in sample means. So we based our confidence interval around whatever this sample difference was that we found. We then said, if we knew the population variances, we could use that standard normal distribution to figure out how many standard deviations away we need to go to the left and right to get our upper and lower bound. And we then multiplied by the standard deviation of the difference in sample means, which we said was basically each sample means variance added together. So we took, right, the first sample means variance, which is just the variance from the first population data we sampled from over our sample size, added that to the variance for our second sample mean, which was the original variance of the data we sampled from population 2 over that sample size. So if we want to build confidence intervals for the difference in sample proportions, it's going to be very, very similar. Right? So instead, we're going to base our confidence interval around whatever the sample difference we find in our proportions is. Right? Which is a little bit different, but not anything crazy. Just like with one population, since we're using proportions, we know we can use the standard normal distribution. We then need to multiply that by the, this is a number of standard deviations. Well, what is our standard deviation for the difference in sample proportions? Well, if we remember, the standard deviation, if we had a one population example, looked like this. Sample size, sorry, this is n. So basically, it's the same idea, or sorry, this isn't the standard deviation, this is the variance. It's basically the same idea as what we were doing with the sample means. We'll take each group's variance of its sample proportions, right? So that would be for group 1. And then we'll add in the variance we would have for group 2. And then we want the standard deviation, so we have to take the square root. So it's really following the exact same kind of setup and procedure. It's just, it looks a little different because we're dealing with proportions now. Sorry, I forgot one of my parentheses right here. Because we're dealing with proportions now instead of sample means. But once we have this formula, right, everything plays out exactly the same. Right? We look the z-value up the same way. We'll be given the sample proportions and our sample sizes. So that's just a matter of plugging our values in. So really kind of the key is still just to find that z-value. Now, hopefully we're using the same alphas, so we should start seeing the same z-values pop up over and over again. Okay. So that's kind of how we, there we go. That's kind of how we arrive, at this confidence interval equation. Okay. Oh, and I'll show it to you guys on the screen here. There we go. Okay. So steps are exactly the same. It's just we have slightly different lower and upper bound equations now. Okay. So let's say we had an example where we had 2 survey years, right? This was, whether or not people were in favor of healthcare coverage for everyone. I think we use this as a 1 population example, but now let's kind of think about if we use this as a 2 population, right? So we have 2 different time periods. We've got pretty high sample sizes in both years. And we want to build a 99% confidence interval. Okay. So the easy part of this is just going to be basically plugging in our values for the sample proportion and the sample sizes, right? So 2011, we had a sample proportion of 0.84, 2010, 0.82. So you can think about it as the sample difference we found here was 0.02. So our confidence interval should be centered around that sample difference we found in proportions. So right away, I can rule out which of these answers. I'm looking at these. I'm building my confidence interval around 0.02. this confidence interval doesn't even include the value of 0.02. Not only is it not in the middle, it's not even in it, right? So we could rule C out here right away. We then, probably gonna run out of room here. Plug in our sample proportion, so 0.84 times 1 minus 0.84 over my sample size from 2011 was 607. I'm gonna run out of room here, so I'm just gonna write it down here, right? But then you would add to that 0.82 times 1 minus 0.82 over the sample size we had for that year, which was 600, okay? So this should be kind of like all in the square root here. Hopefully you're not running out of room wherever you're writing it. So the last thing we have to do is look up, well, how many standard deviations away do we need to go? So I want the 99% confidence interval. So I'm going to go to my standard normal tables. I want to look up alpha divided by 2. So for the 99%, let's see if I can get this back on here. I don't know why that happened. All right, there we go. So look up at my standard normal table, okay? I want alpha divided by 2. So the 99% confidence interval, alpha was 0.01. So divide that by 2, 0.005. Looks like I'm right in between these two values. So negative 2.57, negative 2.58, right? We said the positive and negative already built into our confidence interval equation, so just 2.58. Or we could have used this student T table. We wanted 0.005 in the tail, and if we remembered that, the very last row would have given us our standard normal value. So we can go out to the third decimal if we want to do here, 2.576. Okay. So once we have that, we plug our Z value in, we've got everything that we need. All right. All right, we already had all this kind of written down. Now it's just a matter of plugging in that Z value that gave us alpha over 2 in the tail, and then kind of getting that entered into our calculator. Okay. Any questions over any of the steps here? This should start kind of feeling like we're doing the same thing over and over here. These examples don't really vary a ton, especially when it comes to the confidence intervals. All right, so if I had this confidence interval, what could I say here about the attitudes towards healthcare coverage for everyone, right? Supporting pre-existing conditions, this was not pre-existing conditions, just for everyone. What happened to the attitudes towards that idea between 2011 and 2010? If I'm looking at this confidence interval. With 99% certainty, I could say, all right, I could say absolutely nothing, all right? Because if I'm thinking about that true difference between 2011 and 2010, well, that true difference could be positive, which would imply that 2011 had a higher proportion than 2010. It could be negative, which would imply 2010 is higher than 2011, or it even could be that the views haven't changed at all, right? And that kind of makes sense, right? We did find a positive sample difference here, but it's not that different from 0, right? It's not like we saw 0.1 or 0.2. We didn't see this huge change in the proportion. So just based off the sample, you know, it's very possible that the true difference could be 0, right? Now, it's probably a little bit more likely based off our sample that it is positive, but at the 99% level, we can't say anything with 99% certainty, right? About the relationship between the proportion in these two time periods, okay? So that's how we start interpreting those confidence intervals. Sometimes maybe it helps to like plot this out like this and then think about, oh, there's positive and negative values there. One of the values could be 0. Let's see, hopefully this doesn't, there we go. So we have another example. I'll kind of really won't walk through this one very explicitly. I just want to kind of make a point. I think this is an interesting example when I found this survey. So same time periods, right? So it's the same people, 607 in 2011, 600 in 2010. Here they instead asked not, are you in favor of healthcare coverage for everyone, but do you support the Affordable Care Act? In fact, they actually asked did you have an unfavorable view? So kind of notice from 2010 to 2011, right? The proportion went up by 0.03. So if we're thinking about what we're basing our confidence interval around now, 0.51 minus 0.48, we'd be basing it around 0.03. Okay. So we did see that the Affordable Care Act in this time period became more unfavorable. It's kind of a weird thing here. We're measuring how unfavorable this was, right? And then kind of, right, the Affordable Health Care Act. But what's really interesting about this survey is if we build a confidence interval for this, right, it's going to be the exact same thing. Oh, it looks like, here, let me change the font so this. There you go. So now we got it all in one line. So it's the same steps as before. We identified those two sample portions, our sample sizes. We're building the same confidence level. So if we have the same confidence level, alpha over 2 is going to be exactly the same. We're using the standard normal distribution, so that z value isn't going to change at all. If we build that confidence interval, once again, we can't really say that whether or not this Affordable Health Care Act has become more or less unfavorable, because we've got negative, positive values, and it even includes 0. But I kind of wanted to use this example because it makes an interesting point about how you kind of going back to like our biases. So, notice how high, right, these proportions are. Right? They're about 50%. So about 50% of Indiana residents kind of were in support of the Affordable Health Care Act, 50% weren't. But if you ask the question about what the Affordable Health Care Act really was trying to get at, which was healthcare coverage for everyone, well, that was like over 80% of people were in favor of that, right? And we could get into the minute details. There was other things involved in that act as well, but it is very interesting to see the stark differences just in asking someone about a topic versus asking them about something that actually has a name that they might have heard in their news source, and they know they're not supposed to like it, right? So I thought it's kind of an interesting example. It also gives us kind of two proportions we could start to build these confidence intervals for. And like I said, really, once we start going through these steps, this should start feeling like it's the same thing, right, over and over, right? And we're going to keep finding the same z values because we keep having the same 3 alphas. I don't think it's anything wildly new here. So I think confidence intervals are a little bit easier than proportions. So if we wanted to do a hypothesis test, instead of doing a confidence interval, do a hypothesis test for sample proportions and the difference in sample proportions, we know that our variances are going to be equal to this. Right? We had that from the last slide. However, kind of one of the problems is if we're using, how do I want to phrase this? So if we think about before, when we had one population proportion examples, in our denominator, we were actually going to use our assumed true proportion, right? So before, what we were doing in our denominator, so we had something like this, and we could use our assumed true proportion, right? The problem is now we can think about, okay, how are we going to do this for the difference in sample proportions? Remember, this represents the standard deviation of my sample proportion. So now we're going to be looking at the difference in our sample proportions. So we'll subtract the assumed true difference, which I said last class, I'm always going to give you 0, right? It makes this a little bit easier. And then we'll be dividing by the standard deviation of that difference in sample proportions. Okay. So the reason why we have something slightly different here in the confidence interval than we would for hypothesis testing is because we now have some assumed true difference value. But the issue is our variance is going to depend on both of those sample proportions, and we don't have assumed true values for that. Notice if I assume that that true difference is equal to 0, my sample proportions could be, or sorry, not sample proportions, my, let's say, true population proportions could be what, 0.2 and 0.2. They could be 0.4 and 0.4, right? I only have an assumed true value for this difference, not what the actual values are for each proportion. Okay? So to account for this, we have a slightly different way of calculating the standard deviation for the difference in sample proportions when we're doing a hypothesis test. Does that kind of make sense? So before, we said the assumed true proportion was something like 0.5. That let us know that if that was in fact true, we know what that standard deviation on our sample proportion should be. The problem is now, all we have is an assumed true difference. So if I have the assumed true difference of 0, the proportions could be 0.2 and 0.2, 0.4 and 0.4, any two values that are the same. But if these change, that would actually influence the variance of each sample proportion. So to account for this, we're going to have quite a bit more complicated way of coming up with that standard deviation for our sample proportions. So what it essentially attempts to do is use our sample proportions and kind of weight each one of them, but also factoring in that the sample sizes will also kind of influence those variances on our sample proportions as well. Okay. So we can kind of have an intermediate step here, which is to find this P bar. Now, you could write this all out in the denominator. That just becomes a much more complicated formula to keep track of everything with your parentheses. So here I've kind of set out P bar separately, so you can calculate this first and then plug that in, or just to make the math a little bit easier. If you wanted to write this all out in the denominator, I guess be my guest, but I don't think that's necessarily easier. Right? But other than that test statistic, everything else about hypothesis testing is going to look exactly like what we were doing last class. We had known population variances, and now we have proportions. So both of those situations were examples where we can use that standard normal distribution. So we're going to look up our critical values the same way. We can find p-values the same way. So all the steps are exactly the same. It's just that that equation for the test statistic is going to be a little bit different. Okay. I don't know if people are writing this down, but if you were, I'll give you a little bit more time. Okay. All right, so let's work through an example here. Let's say this was prior to the last election. I went out and I think this was like I believe that Rasmussen was the poll that got the 2016 election correct, or the largest kind of company or whatever that got it correct. So prior to the election, they had 1,500 voters, and 49% said they planned to vote for Biden. 47% said they planned to vote for Trump. If we wanted to test for the this idea that Biden is going to receive more votes than Trump for the upcoming election, what would the null alternative hypothesis be? Well, hopefully when we get to these two population examples, anytime I ask you for a null alternative hypothesis, I'm not trying to trick you. I'm hopefully, I like to think I'm a person of my word, right? But I'm always going to use an assumed true value of 0 here, right? When it comes to these two population examples, I'm always going to use an assumed true difference of 0, right? So right away, you should be thinking A or C, right? Here we want to say, did Biden get more votes than Trump? So really, if it's easier for me to think about it this way, I could say, okay, is the proportion of people who are going to vote for Biden greater than the proportion of people who are going to vote for Trump? Or if I'm thinking about that difference, if the proportion of people who are going to vote for Biden is greater than Trump, what I'm wanting to test for is whether or not that's greater than 0. Okay? Or, I could think about it this way and then just rearrange things so that I have it written out in terms of my difference. And I would see the same thing, which is I'm trying to test for whether or not that difference is greater than 0. So that's my alternative, right? Whatever I'm trying to find, whatever I'm trying to test for, that's my alternative hypothesis. So I've got, is that difference greater than 0? I'll assume the opposite is true, which is that it's less than or equal to 0, right? So here, my null alternative should be A. Any questions on this part? So I know we're kind of new to doing these two population examples, starting to think about how do we identify this null alternative hypothesis. We okay with this? All right. So what type of tail test do we have here? So tell the type of test I have by looking at the alternative hypothesis. I've got a greater than sign. So I've got a greater than or a right tail test, right? So basically what that's saying is, if I have this assumed true difference of 0, and I'm thinking about the distribution of my sample proportions, only evidence on the right-hand side would support the null, right? A sample difference that's positive, and go against that null hypothesis, right? So only evidence on the right-hand side supports the alternative and goes against the null. Okay? So whatever sample difference I find here, I can then turn that into my test statistic, or my Z statistic, since it's coming from a standard normal distribution. And then for a right-tailed test, my p-value would be the probability I saw the test statistic I did, or anything more extreme that would go against my null hypothesis. In this case, that's only things to the right, because I have a right-tailed test. If it was a left-tailed test, I'd have a negative test statistic. The p-value would be the area to the left. If I had a two-tailed test and I saw the same sample evidence, I could find this area to the right, but I have to remember, well, it would have been equally as likely for me to see something that goes against the null on the other side. So I would have to take this area and multiply it by 2. Right? If it was a two-tailed test. It's not. I'm just kind of running through these examples. Right? So here is this matter of now I need to come up with what my test statistic is. So, well, I have critical values here. We'll skip this for a second. So if I want to come up with my test statistic, I know that if I look at Biden sample proportion, it was 0.49, Trump's was 0.47. So I found a positive difference. So I know my test statistic is going to be positive, right? It's on that right side of the distribution. From there, I can't really say anything else about it. 42 seems a little extreme, right? Being 42 standard deviations away from the assumed true difference of 0 seems a little unlikely. But from here, it's just a matter of plugging our values into that test statistic equation, okay? So I've identified everything I need. We could look at critical values here, but I'll come back to this since we skipped it. So here was my test statistic equation. If I plug all of my values in here, so my sample sizes were 1,500. My sample proportions were 0.5. Oh, this doesn't look right. Not 0.52. Oh, wait, sorry. I'm looking at this wrong. My sample proportions were 0.49 and 0.47. So if I plug those values in, that P bar there is 0.48. Okay. So I didn't have those kind of written in there, but all I'm doing is plugging in my sample proportions. And then my sample size for both groups is the same here, so that makes this a little bit easier. So once I have P bar, I can plug that into my equation. I plug in my sample sizes. I plug in my two sample proportions. My assumed true difference is always 0 here in these examples, so that makes that easy. And I come up with a test statistic of 1.097. So this part is really just a matter of computation. Okay. So you're going to have that formula sheet. I'll try to get that up on Canvas even before we go to Thanksgiving break, just so you can start taking a look at it. But right, you'll have that equation on the formula sheet. It's just going to be a matter of plugging our values in. Okay. So once we have that test statistic, what if I wanted to do this test at the 99% confidence level or the 1% significance level? So I want to find the critical value, right, that gives me, well, I don't really want to draw on the same thing here. So I'm going to draw this on a separate sheet of paper. So I want to find the Z value or the critical value that gives me 0.01 in this right tail. Once I find that, for a right tail test, the area to the right would be my rejection region. Okay. So if I want 0.01 in that right tail, when I go to the table, I always have to look up the areas to the left, right? So when I go to the table, I actually would need to look up 1 minus that 0.01 or 0.99, or I can just look up the area of 0.01. But remember, oh yeah, that's going to give me the same value that I need, but it's going to be negative, right? So kind of two ways of approaching that. So I'll go to my standard normal table, or I could use the last row of that T table, right? So I'm going to do it that way because I think that's just a little bit easier. So the area I wanted in the tail was 0.01. I go down to that last row because I know that'll give me my standard normal values. So 2.326, or if I round it to the second decimal, right, 2.33. Okay. Any questions on kind of how I looked that critical value up? I know it gets a little confusing with that T table, using that to look up standard normal values, but using that last row really does make it easier. If you wanted to use the standard normal table, you could have, right? So that would just be finding 0.01 here in the middle. Looks like it's in between these two. So negative 2.32 and negative 2.33. oh, but if I only look up alpha, that's looking at the left side. I wanted the right tail test, so it's that same value of 2.33, but positive, right? Negative 2.33, but positive. So different ways of kind of looking up the same thing, kind of whichever way you find easier to kind of keep track of, that's the way I would suggest kind of doing it moving forward. But once we have that critical value, so we just found what? 2.33 approximately. Well, now I'm just thinking about where's my test statistic fall relative to that critical value. So my critical value is really saying, look, if you find sample evidence that's more than 2.33 standard deviations away from that assumed true difference, then you're okay rejecting, because you're starting to get so far away that it's likely what you assume to be true isn't true. Right? However, we only saw this test statistic, or kind of our Z statistic here. It was like what, 1.09 or something like that, maybe 7, or no, 1.97. I have it right here, 1.097. So we're not in the rejection region, right? So we would fail to reject the null here, okay? So if we go back and remember what the null was, we were saying, is that difference, we assumed it was less than or equal to 0. Okay? Now we saw sample evidence that went against that, but not very much. So we failed to reject it, right? We weren't in the rejection region. Well, remember, this difference just represented the difference between the votes for Biden, the proportion of votes for Trump. So here we couldn't actually say that Trump was going to receive, or sorry, we failed to reject that Trump is going to receive more votes than Biden here. Right? Now, this example kind of points out, let me see here. All right, so we cannot reject the null. So this example really points out that when we're trying to find differences in proportions, it actually becomes pretty tough to reject the null, even if we have pretty high sample sizes. And that's because if you think about it, like especially with these political examples, when you're talking about proportion differences of 2 or 3%, I mean, that's actually considered a pretty wide margin, right? But our sample evidence, we're not going to like see these really extremely large differences, right? We're not going to see difference of 0.1 or 0.2. And so it becomes kind of hard, right? We've really got to find pretty strong sample evidence for this difference, or really a big gap in those sample proportions, in order to be able to reject our null in these situations. So that's why it's hard to predict elections, just based off of samples, even if you get samples that are pretty high. Although I would kind of argue what's probably one tool we could use to get really, really high sample sizes, instead of calling people or sending out mailers now, the internet seems like it'd be a pretty useful resource. Now you might be considered about, people faking the data or something like that. But if we could collect data really quickly and get this up to like 15,000, well, what would 15,000 do? If my sample sizes get larger here, that would greatly reduce, right, this guy right here. So my denominator would be a lot smaller. So if my denominator here is a lot smaller, my test statistic would shoot up really quickly. If I have a higher test statistic, that means I'm going to have a higher test statistic, means I'm going to get a smaller p-value. The smaller my p-value gets, the more likely that my p-value is going to be less than alpha. Right? So we'll start thinking through these lines of logic with hypothesis testing. So I'm going to write this out so I can kind of make this point here, because I think it's important. So here is our test statistic equation. Here's p bar times 1 minus p bar, and then 1 over both the sample sizes. Okay. So the idea was, why is taking higher samples so good? Well, if we recall, what's in this denominator was the standard deviation for the difference in our sample proportions. So if and I'll do this in blue to kind of walk through. If I increase my sample sizes, right, I make these denominators larger here, that's going to drive down the variance I see on those sample differences. And that kind of makes sense. If I have more data, then the sample proportions I see are just, it's more likely they're going to be close to whatever the actual difference in proportions is. Right? If I'm only looking at 10 people, I could have a very skewed sample. If I've got 10,000, way less likely it's going to be skewed from the actual population value. So as that standard deviation goes down, right, my denominator is getting smaller here. That increases my test statistic. If my test statistic is getting larger, then the area to the right of it is getting smaller. So my test statistic is going to get larger. My p-value is going to get smaller. My p-value is smaller. It's more likely it's going to be less than alpha, which is when I can reject. So that p-value getting smaller, we would then say, I'm more likely to reject here. Okay. There might have been a question kind of like this on one of the practice exams. I don't think I asked you something like that on the exam, but for the final, something like this would be fair game, right? So if I take a higher sample size, which of the following is going to happen? Well, my test statistics should go up, my p-value should get smaller, and it's going to be more likely that I can reject the null. Okay. Any questions on that one before we keep moving here? All right, so let's say we go back. Actually, I don't really like this example. I think do I have one more? No, I don't. So I guess I have to like this example for right now. So let's say we went back to that survey, Indiana survey, said, is the views of healthcare, supporting healthcare coverage for everyone, have they changed from 2010 to 2011? So if I just want to know, have these views changed? Are the views different than they were the prior year? I'm just thinking about, are these proportions not equal to each other, or is the difference anything other than zero? Right? If I'm saying are views different in these two time periods, what I'm really saying is the difference between them anything other than zero? So I assume the opposite is true in my null, which is that it's exactly equal to zero. Okay. So here, let me go back here for a second. Since you guys are here today, kind of use this, give me an idea about where we're at with hypothesis testing. Starting to get a little bit, few glossy eyes out there. So I want to kind of make sure that, or at least, hopefully it's not because you're lost, but hopefully because this is becoming pretty repetitive, right? We are using the same steps over and over. We'll get away from it here soon. I promise we'll do some more interesting stuff with linear regression, right? So remember, I have a two-tailed test here. And if I wanted to build the confidence interval at the 1% significance level, right? So this is like the 99% confidence level. I could determine what my alpha value is. I could then think about, for a two-tailed test, how would I find my critical values? All right, I'm going to have two values, one on each side. All right, so I'll give you a little bit of time to kind of look those up. You've got kind of those Z tables in front of you, or pull them up on your phone at the files on Canvas. Or we could think about, when we were doing a one-tailed test, we found the critical value was 2.33. So knowing that, you actually could determine what the critical values for a two-tailed test would be at that same level. I mean, you wouldn't know the exact value, but based off of these four, you should actually know what your critical values should be. Right? So once again, if you have the tables in front of you, that makes it a little bit easier. But if you didn't, remember, we found the critical value for the 1% significance level for a one-tailed test was 2.33. So knowing that, you actually could determine which of these four answers would give you the critical values for a two-tailed test. I'll give you a little bit of time to kind of work on that one, and we'll talk about it. All right. So if you don't have an answer, take your best guess here. And we'll kind of talk about this. So there's 24. I think I counted 27, but all right. I'm going to close it out. Maybe I counted one off. So I'm looking for critical values here, right? So these are like my cutoff values to create these rejection regions. Okay. If for a one-tailed test, when I wanted alpha in the tail, that was a critical value of 2.33. If I have a two-tailed test, how much is in each tail? Alpha divided by 2, right? So 0.005. So how would I get a smaller area in my tail here? My critical value would have to be relative to 2.33, my critical value would have to be higher. Yeah, someone's pointing up, right? Think about it this way. If I know that for a one-tailed test, to get an area of 0.01, that critical value was 2.33. When I want a two-tailed test, I want alpha over 2, right? Or 0.01 over 2. So 0.005 in each tail. The only way I can do that is if my critical values are a little bit higher, right? So if I go back and I look at those possible answers, the only thing that's higher than 2.33 there is that 2.576. Okay. Now, if I gave you other values that were higher, right, we could do this two ways. So I think the values I have displayed here, if I wanted 0.01 over 2 or alpha over 2 in each tail, that's 0.005. I could use the very last row of that student T table to get that 2.576. And it's a two-tailed test, so it's positive and negative, right? I've got a pair of critical values for a two-tailed test. I could have also used the Z tables, tried to look up 0.005. Oh, where is it? Right here. I can get pretty close. So negative 2.57 and negative 2.58. So I'm somewhere in between, right? So 2.58 to the second decimal, positive and negative. Or, I displayed the answers at the third decimal, but if you would have looked it up and found 2.58, hopefully you could have realized that, yeah, you're only off at one decimal, but right, this should clearly be the right answer. And it's not like I would give you 2.57 and 2.58 as two potential answers there, right? Wouldn't make rounding kind of result in you not identifying a correct answer. Okay. Any questions on that one? I'm somewhat afraid to look at this, but all right. So a lot of people went with kind of that 2.3, right? So that's if we have a one-tailed test, then we would just look up alpha, right? Because alpha is total going to be what's in our tail, right? If we have a two-tailed test, alpha is the total area in our tails, right? So that means we have alpha over 2 in each tail. So that's the value that we need to look up. That's the area in the tail that we want, okay? So hopefully as we kind of keep working through more and more examples like this, these critical values will become kind of the easier part. I think for hypothesis testing, probably the critical values, once we get good at identifying what distribution we should use. And up to this point, for the two population examples, we've only used the standard normal, right? So at least up to this point, that critical value kind of method should start to hopefully kind of sink in. The two-tailed test is a little bit different. We have to be careful about that. But as we see more examples, I think that'll become a little bit easier. So I then could come up with my test statistic. Once again, the test statistic is really just going to be a matter of computation. I've got my two sample proportions. I've got my two sample sizes. So that's just going to be a matter of plugging all of my values in. So 0.84 and 0.82 are my two sample proportions. 607 and 600 are my two sample sizes. I can come up with P bar. So that ends up being 0.83. Plug in P bar, 1 minus P bar, or 1 minus 0.83. My sample sizes, my sample proportions that assume true difference. I'm always using 0 here for these two population examples. So I should get a test statistic of about 0.925, which if I think about where that's at relative to my critical value, actually, I think I had two critical values here, right? 0.09 as my test statistic. I'm nowhere even close. Wait, what was this? Sorry, 0.925. I'm nowhere close to those rejection regions. So I here would fail to reject that the differences in how people viewed healthcare coverage for everyone, I fail to reject that they've changed at all, right? That difference is actually 0. Okay. And that kind of makes sense. We didn't find very strong evidence that they've changed, right? It was 0.02 difference, kind of like with the previous example. So we didn't have very strong evidence that there was actually any difference between those 2 time periods. Okay. Any questions over anything here? So we've got how much time left here? About 10 minutes. So we'll start kind of looking at this in Excel. Eventually, I didn't put up the next Excel assignment because I forgot that what we worked on Monday wasn't actually part of one of the questions on it. So what we start doing today will kind of be the very first question on that Excel assignment. So I'll get that posted this afternoon. If you want to start to kind of chip away at that. So let's see, I've got, we started this last class. Did I save it here? Yeah, I saved it, sweet. So we had all of the work that we did last class, looking at the difference between the South and the Midwest enrollment, okay? So now we're gonna look at a proportion example, okay? So for the Midwest, right, that we had on a different sheet, I can come up with a sample proportion for whether or not the school had more female than male students, right? So the proportion of schools that had more female versus male students. This variable that I have that identifies that is just a 1 if they did and a 0 if they didn't, right? I guess you can kind of see here with the data. So right, if males undergraduate enrollment was less than female, then that's a 1, right? That means they had more female undergraduates. If males were greater than female undergraduate enrollment, that would just be a 0. So if I want to find a sample proportion and I have this 1, 0 variable, it's as simple as finding the mean of that 1, 0 variable. Okay, so I would select that entire column of data. I'll use that count function to get my sample size, right? And at least to the second decimal here, it looks like about 3/4 of schools in the Midwest have more female than male students. Okay. I then go to my South worksheet, and I'm going to use that little thing where I want to take the Midwest values and put them over here on this sheet, right? So that was just a matter of putting that equal sign, clicking on the sheet that I wanted to grab the value from, and then clicking on the cell that has that value in it. And now I've got the Midwest values here. Okay. Let me make this, there we go. So now I'm gonna do the same thing, but for my Southern schools. So I've got that variable over here, whoops. So I'm gonna find the average. That should just give me the sample proportion of schools in the South that have more females than males, right? In terms of undergraduates. I can use the count function to find my sample size. And now I've got my 2 sample proportions and 2 sample sizes. I can start to build things like confidence intervals or do some hypothesis testing. Okay. So one thing, let me go back here, that we did earlier is we had this equation for our confidence intervals. So what I'm going to do in Excel is calculate this standard deviation in a separate cell. That way I don't have to enter it in a whole bunch of times, okay? So all that's going to be, let me see if I can get everything here on the screen. So we'll take the square root of the first group's sample proportion times 1 minus that group's sample proportion, and then divide that by, I think the sample size here is an R5, right? And then add to that the second group's sample proportion times 1 minus that group's sample proportion divided by their sample size, which is in S5. So all I'm doing is using Excel to be my calculator here. It's a lot easier than dealing with proportions, especially if I wanted to, 0.85507, right? I don't have to keep entering this into a calculator. It makes this quite a bit easier, right? So now I've got that standard deviation for the difference in my sample proportions. From there, kind of the key is, well, now I just need to find that Z value that gives me alpha over 2 in each tail. So go down here. How would I do that? Well, just like what we did last class with the sample means, I'm going to use the standard normal distribution, but I'm working in reverse or the inverse, right? I know the area of the tail I want to find the z-value. So the area I wanted in the tail was alpha, or I said in the tail, sorry, on each side of my confidence interval. I can think about them as tails, but, all right, so alpha over 2. Now, this is always going to give me the negative value because it's looking at that lower left tail. It's already built into my confidence interval, the positive and negative sign. So I'm just going to take the absolute value. This is exactly what we did last class, right? The exact same thing we have up here. So I should have the exact same z values for my confidence intervals I did before. From here, it's using Excel to bear a calculator, and it should be a pretty quick, easy kind of equation, I guess, right? I'm going to take the difference in my sample proportions, okay? So group 1 minus group 2. I'm going to subtract a certain number of standard deviations away that I want to go to get that lower bound, multiplied by what the standard deviation for that difference in proportions actually is, okay? Now, if I want to copy this down for different confidence levels, everything's going to be exactly the same. It's just I'm going to go a higher number of standard deviations away. So the only thing I want to change when I copy this down is this z value, right? So I'm going to freeze every other cell reference, hit enter, and I'm going to copy this down. Okay. Then to get my upper bound, I'm going to copy this equation, hit enter to get out of the cell, paste it, and remember, the only thing that changes, I'm now adding my margin of error. Okay. Once I have that, and copy this and kind of get my confidence intervals here. Now, we can't say at the 90% level here, so I'll change something to just kind of point out because it is kind of interesting, right? I have negative and positive values here for this difference in my sample proportions. I even includes the value of 0. Well, let's say instead of like the 10% significance level, I wanted to do the 12, right? Oops, 12, which would be an alpha of 0.12. Well, maybe not, 0.13. 0.15, that should be enough. There we go, right? So if I wanted to say this with 85% confidence, which isn't 90, but you know, it's not 50 or 60, with 85% confidence, I would have a confidence interval that only includes positive values. So with 85% confidence, I could say, where was it? That Southern schools tend to have kind of a higher proportion of females relative to male students than the Midwestern schools, right? And that plays out if I just look at the sample proportions, right? It was quite a bit higher, right? But once again, with proportions, it's really hard to be able to kind of reject the null, or really hard to get a confidence interval that only includes either positive or only includes only negative values. So that was kind of another example of this here. Okay. So on Friday, we'll do hypothesis testing in Excel for proportions. We'll then start looking at the difference in sample means with only sample variances. I'll get that Excel assignment up later this afternoon. And I'll probably get the next Connect assignment up there as well. Actually, I might have already posted that yesterday. I can't remember if I had set it to release yesterday or today. But you'll have those two. Start working on those so you don't save all the work for like the last minute. And then it's 2 weeks after, you know, we started covering this stuff. Okay. All right. I'll see you guys on Friday.